So if you don't apply the activation function in the output layer, your neural network model work as a regressor. If I apply the activation function in the output layer, my neural network model work as a classifier. Because once you apply the activation function in the form of a sigmoid, what happens? 1 divided by 1 plus e to the power minus of w1 x1, w2 x2, plus etc. up to w. If you have p neurons, just immediately before your output layer, this is output layer, my immediate previous hidden layer has some p neurons. Okay, so you have these p values, p neurons. So that means your wp xp plus finally I will have one bias wb. In analogical comparison, this is similar to your intercept. So what will happen? The sigmoidal function will map this numerical quantity to 0 to 1 scale as a probability score. Whereas for the multi-class problem, you don't have one neuron in the output, you will have a multiple neuron in the outputs. So your each classes will be one hot encoded. So what is the drawback of sigmoidal activation function? See, even if I apply the same sigmoidal activation function for multiple neurons in the output layer, what will happen? The sum of these probability will not be equal to these probability, because the whole equation is going to give me 0 to 1. That is a nature of it. It will squeeze the continuous value to 0 to 1 scale. So for 2 neurons, your sum of the probability will come to 1. But if it is more than 2 neurons for the multi-class, you will have done one hot encoded the labels. In that case, the sum of the probability is not equal to 1. In that case, what we do, we apply softmax. What is a softmax? Softmax is nothing but exponential normalization of your sigmoidal activation function. So as usual, you apply sigmoidal activation function in the each output neuron, and you may get some score like this. Say for example, 0.91, 0.32, 0.15. Now, if you see, the sum of these values is exceeding 1. Okay, whenever I have more than 2 neurons. So to normalize these scores, what the softmax is going to do, e to the power 0.91 divided by e to the power 0.91 plus e to the power 0.32 plus e to the power 0.15. So that is why if you see model.compile, whenever we apply for multi-class problem, and we have applied the activation function as a softmax. For binary class, we have applied the activation function as a sigmoid in the output layer. Whereas the intermediate layers, your hidden layers and all, we have used ReLU activation function. The reason is we have discussed whenever we use a sigmoidal activation function in the hidden layer, what is the issue we have is because the sigmoidal function has this is a saturation zones, and when we calculate the delta term derivative of the saturation zones, it will reach to very negligible value, because the constant, this is almost like a constant. If you derivate this derivative term, delta term will almost approximate to 0.0000, very negligible value. And this term, if you propagate it back to calculate the delta hidden 1, delta hidden 2, and so on, these values are very negligible, and it's hardly contribute to the changes in the weight update. So it is hardly contributing any changes. That's why we call this a vanishing gradient problem. To avoid that, we introduce ReLU activation function in all the hidden layer, but only in the output layer, either we use the sigmoidal activation function or softmax activation function according to binary or multi-class. So this is what typically your design consideration whenever you do with feed-forward models. So all feed-forward models are either used as a regressor model or as a binary class classification model or a multi-class classification model. Typically, what we have used, what are all the applications we have done using these models? One is sklearn. Using a sklearn library, you can use MLP classifier. Using sklearn library, we have used MLP regressor, the house price prediction. You can solve using this MLP regressor. And for the classification, diabetes class predictions, you have used. So what is the limitation factor of sklearn MLP classifier and sklearn MLP regressor is, the limitation is I cannot feed other than tabular data set. So here my only constraint is I have to pass only tabular data set. That means I have to pass only n cross p data, like first record with all the features, second record with all the features. That means I have a limitation here to work with images or to work with time series data set, to work with the text data. I have a limitation because directly I cannot feed image, or directly I cannot feed I cannot feed a 2D, or I cannot feed a time series, or I cannot directly feed a text. So that is a bottleneck of using sklearn version. Number two, we have moved to TensorFlow and Keras. TensorFlow, Keras. In TensorFlow Keras architecture, we have additional layers called convolution 2D, convolution 1D. That was our last previous few sessions, maybe 4 sessions, I can say. It is based on how to design convolution 2D design for the image dataset. And the previous session we have discussed for how to use classify. Last 2 sessions we have seen how to classify the time series data. We have classified EEG signal, brain signal. One is alcoholic, another one is a non-alcoholic. They are time series data set. We applied one-dimensional convolution because we know that time series data is highly redundant. Whenever I presented convolution 1D, my output of convolution 1D will be acted as my feature space, and we applied max pool. We downsized this vector to half according to your max pool dimension. When you say 2:1 means it will downsize to half. If you feel there are too many samples are there, you can say downsize to 4:1. That is what your max pool will do. Finally, the output of the max pool layer we will feed as an input to your fully connected architecture. So your TensorFlow Keras framework will facilitate your image data, your time series data set, even text data set. Particularly in the last 2 sessions, we were worked mainly on the text data set. We have seen so many pre-processing techniques, how to prepare a text data set as a simple count vectorizer. Okay, for example, if I have one review, simply that review is made up of, first of all, I create all the tokens, the corpus of all the tokens. Imagine I have totally 100 reviews. Put together all 100 reviews. It can be some movie review, or it can be a product review, or it can be some hotel service review, whatever it is. And put together all 100 reviews, we have a corpus of tokens. That means a unique keywords. Other than, we have filtered out all the English stop words like is, of, preposition, conjunctions, all these English stop words, usual English stop words, conjunctions, everything we have filtered out. Afterwards, we have the unique keywords as the tokens, and we have various ways we represented the text. One is a simple count vectorizer. Simply, it just counts the frequency. For example, the first product description is made up of, maybe it's a mobile phone, and it has a description about one of the keyword is like maybe a RAM or battery. Okay, maybe processor. We have so many keywords. And the first product specification, there are 2 times the RAM is being defined, and screen battery is being defined as 2 times, and the screen has been defined. Its display size is 4.7-inch display. Some one of the token can be a display. Another token, it's like I can say amyloid. If it is an amyloid display, again amyloid is being used 2 times. And LCD is a keyword. LCD, this product does not have a LCD display. It's an amyloid display 2 times. Likewise, it's a comprehensive list of all the keywords. Not necessarily that every product will have the occurrence of these keywords will occur. Like all the 100 reviews we have tokenized like this, and we represent as a tabular structure. This is called a simple count vectorizer. So we understood this is not an effective scenario. So what we have later, I introduced TF IDF vectorization. What is this TF IDF vectorization? Along with your this count is nothing but your term frequency. Your term is nothing but this token is considered as a term or a keyword. How many times this term is occurred in that review? That is what the term frequency. So the number 2 is the term frequency here. That is being scaled by inverse document frequency, IDF. So what is this IDF? So this particular, say for example, one of the keyword, one of the term is being appearing in all the 100 product. If that keyword is appearing in all 100, I need to consider that keyword is not a unique feature or a significant feature. So in that case, my inverse document frequency term would be calculated like this: log base 2. Okay. For example, this keyword is appearing, okay, out of the 100 reviews, it is appearing in only 10 reviews out of the 100 reviews. So this is the weighting factor for IDF weighting factor for this keyword. So whatever the term frequency I do the count for example, the first product, this term, there are the 3 times that this word is appearing. That should be scaled by this IDF term. How this IDF term, what is the weighting factor for this keyword? How do I compute? Log base 2. Okay, totally this term is appearing in 10 product out of the 100 products. So this is the weighting factor. On the other hand, assume this feature is this term is it's appearing in almost all the product. Okay, this description is this particular token is almost coming in all the product. What is the IDF factor for this term? Log base 2, 100 divided by 100. What happens? Log 1. Log 1, 0. That means however number of times this term is appearing, maybe 4 times, it's multiplied by 0. That means this IDF factor is going to reduce the significance of this frequency, significance of that particular token. So we have used TF IDF factorization. Also, I have introduced the most advanced word embedding. Word embedding. In word embedding, what happened? No, each and every token is not represented as just by the frequency of occurrence. Rather, it is being represented as a feature map. Feature map. For example, say for example, one of the token is maybe LCD. LCD is being defined as whether it is an animal, or it is a eatable a food item, or it is a electronic gadget. Likewise, each and every word available in the English dictionary is being defined as a, okay, it is being defined as a vectorized form. Okay, for example, vectorized with a weighting form also. So definitely LCD is not a food item. So the weighting factor LCD for the food item, it will be 0. Electronic, it is giving some weighting factor. Okay, LCD, the token LCD belongs to electronics with some weighting factor 0.8. Again, another feature may be display. The LCD, okay, which belongs to the display feature, it is around 0.9 weighting factor. Whether the LCD is an animal, again the weighting factor is 0. So this is what the word embedding. So there are different companies. They have their own unique word embedding. That is, so the product to product, the number of feature description will vary. Okay, for example, Google uses a BERT, BERT, BERT word embedding, and Facebook uses news word embedding. So according one company to another company, each company, the only difference is a particular company product will define each and every token with 100 features maximum. Some product will describe each and every token with 200 features. So the maximum is limit is 1000 features. So almost all the product nowadays which is available in the market is try to describe each token with 100 features. So instead of representing your text with a simple frequency as a simple count vectorizer, or which improved count vector weighted value with IDF TF IDF vectorizer, and representing your each and every token with a vectorized form is the most recent way to represent your text. So your TensorFlow and Keras framework can accept your image, pre-process the image in the form of a convolution 2D. If it is a time series, it will pre-process in the form of a convolution 1D. If it is a text, we can pre-process in any one of these formats. And the most advanced format is a word embedding. Using word embedding only in the last session, we have done the sentiment analysis for the classification task. At the end of the day, so far, the application, whatever the application we have seen, okay, using the feed forward models, typically used for the prediction, okay, particularly on the classification context. If it is an image, we have classified the images. If it is a text, we have classified the text. If it is a time series data set, we have classified whether it is an alcoholic EEG or it is a non-alcoholic EEG. So mainly the target application is a classification. Okay, when it comes to feedback based model, okay, your architecture is going to be something like this. Okay, your input. Here, if you see in the feed forward architecture, you have input layer, hidden layer, output layer. It is only feed forward architecture. Though we propagate the error backward, that is the your d minus o into 1 minus o. This is the term we propagate backward via this weight matrix, just to calculate the error gradient, okay, to update the weights in the hidden layer. But your model architecture is it's a feed forward architecture. Then what kind of architecture we say it's a feedback model is? Okay, your output, whatever your previous state output, I will be feedback to the input. That is typically is called as a feedback architecture. So from the agenda for hereafter, from the 9th session moving forward for the next 3-4 session, maybe next 4 session, I guess, we'll be working on feedback based model. That is a recurrent neural network. In recurrent neural network, what happened, along with your current input, your previous state output also will come as the input for your model. Of course, we are going to see the detailed mathematics behind, like the way how we understood the feed forward model. We'll be go through the complete mathematics and the working idea of the recurrent neural network model. Just I'm giving you the overview about what is the usage of this recurrent neural network model. So why we need these kind of model? So these recurrent neural network model is specially designed for specialized applications. We don't use recurrent neural network model for the classification. First of all, we don't use recurrent neural network for classification application. For classification applications, already we have done enough number of model design using a feed forward architecture. Then why we need this? For what kind of special applications we need a recurrent neural network is? Number one, for time series forecasting. Number two, for text data sequence forecasting. In fact, the more number of applications, the prominent applications currently available in the market in recurrent neural network is, okay, the more customized version of the recurrent neural network we used to call as long short-term memory, LSTM. So once you understand the mathematics, you will understand why a recurrent neural network is being customized to, because there is a limitation of this recurrent neural network, traditional recurrent neural network. To overcome that limitation, there is a small fine tuning is done in the architecture. Because of that fine tuning, okay, your traditional recurrent neural network architecture is being specifically called as long short-term memory. So this is what the more commercialized version of the recurrent neural network model we used, which is very popular for the text application. Of course, for the numerical data application, only on the time series data forecasting. Other than the numerical data, if you see where are all the places your LSTM model is very popular on the text. In text, we use this model for the sequence of forecasting. The very well-known application is when we type our text messages in our mobile phone. The moment you type a word, it is going to give you the next few keywords to you, right? That is a classic example of the sequence forecasting application. The actual algorithm working behind the scene is long short-term memory model. And also nowadays, even in the email also, when you try to reply to an email, we try to do the autocomplete for you. So the moment you say good morning, and you see this, the people are trying to improvise the model. Sometimes they ask you some feedback and suggestions. I don't know how many of you have given the feedback and suggestion to the Gmail. I personally used to give a lot of feedback and suggestions. Sometimes the model does not notice the time zones. Hope you have seen it many times. Because when suppose you are in the Indian time zone and in the evening hours, you are trying to reply an email. In an evening hour, when you try to reply an email in the evening hour, the LSTM model does not consider the time as one of the feature. It does not consider the time zone. Always by default, it try to say the moment you type good, it always do the autocomplete with morning. So now they are trying to improvise the model. Okay, not that sequence the English words after these words. Next, what are all the words should come? First, they generate all the possible sequences. Okay, what is my input word? What should be the output word I should map? For this input word, what should be the output word? So there are many mapping we used to do in the sequence mapping, like two word to one word mapping, two input word, one output word, three input word, one output word. So there are multiple ways to design these architectures. So moving forward, our exercise will be designed on sequence forecasting application design. We'll be talking about such. So what are all the different way I can generate these sequences? I can prepare my training samples, one word to one word mapping, or two word to one word mapping, or three word to two word mapping, or two word to two word mapping. There are different way I can prepare my training samples, so that once my model is being trained, so once you started typing the reply, it is trying to give you the autocomplete for it. So how that is possible? Because of the feedback type architecture, which has the sequence context. Whereas here there is no such a sequence context, isn't it? So you present one feature, you present second feature, the third feature, there is no connection. Okay, I should present the second feature only after the first feature. There is no criteria. But here, the time series data set, your sequence having a context. Similarly, your word, your sentences. Okay, after this word should come. After this word should come. We have a sequential context attached to it. Whenever you have a sequential context, we prefer to use a feedback-based architecture, that is a recurrent. So this is one application. Sequence forecasting. Another popular application is the extension of the sequence forecasting, one language to another language. We call that as a machine translation. Machine translation application. So we have so many softwares, even in the Google machine translations. You wanted to convert your English to French or French to English or German to English, we translate. Input words you present in German and it is mapping to the output as English. Again, okay, a sequence of foreign language to the sequence of English language mapping. So how do you tune the architecture according to this particular application? So application to application, the way in which you design your LSTM architecture slightly modifies. So we don't design the similar manner. If my application is a sequence forecasting, my design of LSTM is slightly different. If my application is one language to another language mapping, my design is slightly different for that kind of application, machine translation. Another application is image captioning application. Another interesting application. In the image captioning application, once again, for example, if I present one picture to my model, okay, there is a boy playing in a seashore, okay, a boy playing in a seashore with a football. The moment I present this image to my model, okay, my model should give me the output in the word sequence. This is called image captioning. Again, my LSTM model is going to work here. My model is going to say that, okay, output is boy, okay, playing soccer in seashore. My input is image, but my output is a word sequence. Again, this is a special unique application. Image to word sequence. This is called the word captioning or image captioning. Some crowd watching soccer. In that picture, if I present, my model will say that, okay, a group of audience watching soccer game. So according to the context of the image, my model is going to give me the word sequence. So in all these applications, how do we prepare the data to the model is very crucial. How do we prepare the training samples? That is very crucial. And the second crucial aspect is How do I design my model architecture? Most of all the cases, the core algorithm is LSTM model, but application to application, the way in which I customize that model, that is very interesting to see the application changes. My customization of my model architecture design also I'm going to change. The core idea I'm going to take it, and little bit I just play around with the peripherals so that I can bring very interesting applications according to the different nature of my data. So overall, you understand the feedback based model is typically used for forecasting the numbers or the forecasting the words if it is a text. If it is an image, we use it for the image captioning applications. So these are all some of the popular applications. Of course, if you look at, okay, if you ask me, this is the final set of application of LSTM model, because the count is very exhaustive count. So what we have comprehended, if you see whatever is the best possible to be accommodated in the 15 sessions program, that is the best possible way. The maximum application is very popular application, we try to accommodate it. Whichever is beyond the scope of our courses also, there are few applications like a chatbot applications. There are so many other applications also we have not included, but the core idea, once you got the core idea, so the application to applications, what you can say that almost your 90% of the code is going to remain same. If it is a chatbot application, you should know that once you should know the knack, how I have to fine tune the model architecture. Once you solve at least some 3 to 4 applications, you'll get an idea that if it is the you tomorrow, if you end up with some new applications and which portion of the architecture you should change. That idea, if you got, whatever the future some variety of problem you handle in this zone, you could be able to solve it effortlessly. But as of my knowledge, I think I can say that 90% of the applications, exhaustive application, the popular application, the final spectrum of our course is, in fact, I can say the first two, feed forward and feedback architecture, is very matured. Commercially, it is very matured. Many industry successfully they started applying these models for their application. When it comes to reinforcement models, okay, I can say it is in the infant stage. Infant stage, the first two type of architecture is, I can say, they are at the matured level. Your reinforcement model is in the infant stage. Infant stage in the sense they are in the research phase. They are in the research phase, I can say in the academia phase, not to the commercial phase. Some of the popular application, I tell you, some of the popular application which comes in the reinforcement model is the driverless car. You heard about this popular applications are driverless car, the robotic automation. The robotic automation in the sense I can deploy a robot to walk or to play a particular game, or for example to maneuver a robot in a particular closed environment without hitting any obstacle. My robot should learn from the environment and it has to maneuver different obstacles and it has to do some task. So not only to just to walk, I can make my robot to do some task also, to play some soccer game or something like that. So it is typically is going to learn lively from the environment. Instead of feeding a historical data, the idea of the reinforcement learning is all these application is going to take the live data from the environment. That is a unique characteristic of the reinforcement learning. So I cannot use a traditional a feed forward architecture like this, or a feedback architecture like a recurrent neural network or LSTM model. I cannot use it because the application itself very unique here. A driverless car, I can make my artificial intelligence model to play some chess game against the world #1 champion, or I can make an AI model to play some popular game like AlphaGo. These are all some of the things you have heard. Driverless car in a closed environment. How my model is going to learn in a closed environment, learn from the surroundings, and gathering the live data, how my model is going to optimize the task. Again, this is a new set of algorithm we are going to learn under the reinforcement learning. Maybe you are, I think, 12, 13, 14, session 12, 13, 14. I think your next week, Saturday, it's the whole Saturday forenoon, two session, and in the afternoon session is purely on your reinforcement learning. You'll be start from the scratch. What are all the components of the reinforcement learning? How to build a reinforcement learning from the scratch for a variety of applications. A couple of case studies I have done. Session number 12 to understand all the component of reinforcement learning, and 13 and 14 are the implementation. One for the robotic application, another for some. I have taken one case study on some stock market, I guess. So trading. So how to deploy a model for the trading, automatic trading, because when the trading happens, model has to understand the live environment of the trading, and accordingly the model will going to do the trading instead of the expert who do the trading.
Mahesh,
And finally, yeah,
I have one question. In this reinforced learning models, how the training will take place since it's going to work lively. So how we go for the training phase?
yeah, definitely, Shyam. We'll be discussing in detail. There are some algorithm which is going to popular algorithms are there, which is going to we use those algorithms to train the data. Okay. See, once again, when it comes to the algorithm, I may use the traditionally available models, but along with optimization technique, what I can say, ANN plus optimization technique is going to play a role. Instead of running a standalone ANN, here I'll be running a neural network model along with optimization technique. Like we have so many optimization technique, like traditionally we have some stochastic optimization technique, um, like linear programming and traveling salesman optimization technique, even some biologically inspired optimization technique like a genetic algorithm, particle swarm optimization. Of course, a genetic algorithm, PSO, anti-colony and all, it is in the research level. Still, it is not people, they started applying in commercial models as of now. Maybe in future models of the reinforcement learning will incorporate these kind of optimization technique also, incorporate along with your existing architecture. But as of now, they use some standard algorithms, optimization algorithms. So we'll be discussing in detail what are all the popular algorithms they use in the current reinforcement learning model, which is being utilized in certain prototypes. Because though these driverless car or these robotic applications are not successfully used as a commercial product, but some prototypes they have developed. There are so many companies, they have developed those prototypes. For the prototypes, which algorithm they have used, I will be using those algorithms for the demonstration. Just to quickly highlight those algorithms which is being currently people are using for some of the prototypes, or this is the deep q learning. This is one of the popular algorithms, and all the idea came from Markov decision process. The fundamental, the maths behind all these optimization technique came from Markov decision process. So we'll be learning these mathematics of Markov decision process and what is exploration, exploitation. Um, so the core idea is some of the popular algorithms. These are all the typical algorithms. Deep Q, another one is PPO, another one is A to C. So these are all some of the algorithm. Of course, we'll be learning in detail about how these algorithm works. Basically, the fundamental idea of all these algorithms is underlying philosophy is the optimization functions, how this algorithm is going to reduce the cost function of these optimization algorithms. So if you see the session 12, 13, 14 is all completely working on the reinforcement learning. And of course, the final session is on the transfer learning application. So in a broader perspective, your whole AI algorithm, you can broadly categorize into three major categories: feed forward, feedback based, and the reinforcement models. And again, I'm telling you, the reinforcement model or in the prototype level only, it is not in a no for any successful commercial models. It is not there, but prototype level demonstration people have done. But other things we are very well aware of, the successful commercial products are available in the feed forward and the feedback models. So in the future developments in the AI development will be happening only in the reinforcement learning. And also in these cases, what are all the feature development can happen is the research is moving on more explainable models. Explainable models. As of now, these models are not explainable. So the research focus are in the direction, whenever you construct a complex model with so many hidden layers, your model is not explainable. How better we can explore the hidden layer weights in an explainable manner? What are all the possibilities we can try to leverage the hidden layer weight value to be explainable? So in that direction, the research or people have initiated the research work to have more and more explainable AI models in these cases. And in these cases, the research focus is on, so how to convert a prototype into a commercially viable models. So that is how the research is going on, how to converting these prototype into viable commercial models for the end user. So the complete picture of all three cases I have given. Now let us focus on to the agenda of the context for the why we need a recurrent neural network model for the time series data set. First, we are going to work on numerical data set. Then we'll be subsequently we'll be moving on to the text data set for the word sequence application. To start with the text, to start with the time series data set. So typically the nature of a time series data set, let me take some data like a temperature, a daily temperature. I have taken the 1st January temperature, 32 degrees Celsius of some Indian city, let us assume. 2nd January, we have 33 degrees Celsius. 3rd January, we have 31 degrees Celsius. 4th January, we have again 32 degrees Celsius. 5th Jan, we have 32.5. 6th Jan, we have 31.8. Likewise, how people initially worked on the time series data sets before the recurrent neural network idea came. What they have done, simply they just created the time lag. See, for example, if I wanted to predict the 3rd day temperature, that means the 3rd June temperature. Okay, why don't I use the previous 2-day temperature? That was the initial thought process. People have created just a time lag. So they try to use t-1 and t-2 to predict the time state t. Okay. So your data will be presented in a single column. Generally your time series data will be in a single column, which is the timestamp. There are so many applications your time series data set. Like I have a sales data set. Imagine a particular company or a particular product is maintaining a sales figure. Maybe it could be a daily sales figure, or it could be a weekly report, or it can be a monthly, whatever it is, a sales figure. So in terms of volume, okay, on the particular timestamp, what is the volume? How many volumes? On a particular another timestamp, what is the volume? Another timestamp, what is the volume? It could be a sales figure, or it could be some sensor data like a temperature or some pressure monitoring, or some kind of some force monitoring, some kind of a sensor which is continuously monitoring certain time-based monitoring, any sensor. I can even, you can say your trading, your stock trading. So different hourly, okay, what is the trading happens hourly trading if you have these time stamped the trading pattern of a particular stock value. Maybe a gold price, daily gold prices or fuel prices. These are all some of the examples which comes under the time series data set. These time series data set, first of all, I create a lag. So how to decide the lag is based on, okay, with what lag my time series data is highly correlated. Typically, they take that lag. So for that, what they do, first they convert a single column data into a multiple column data according to the number of lags they take. For example, this single column data, if they prepare it like this, with the previous 2-day time lag, they could have prepared the data set something like this. For example, 32, to start with the 32 degrees Celsius, I don't have a previous 2-day information. 31st December data and the 30th December data, I don't have, assume, because my data starts from the 1st January. Since I don't have a 31st December and 30th December data, I simply fill this with a 0. Okay. Next, for 33, I have, okay, only 1st Jan data. I don't have 31st December data. Okay. So what people they do, simply they discard the first 2 record. They start considering from the 3rd Jan record. So 31 degrees Celsius, the previous 2 data will be 33 and 32, the previous 2 time lag, and 32.5. Okay, now you can see, for to predict 32.5, your previous day output also come as one of the input. That is what we take a concept of feedback model. In feedback model, because to predict the next time state, okay, my previous state output also come as one of the input. In this case, this 33 will be going here, 33. Along with that, your previous day temperature is 31. And to predict 31.8, my previous 2, that means my previous state output will come as one of the input. Okay, along with this input also will come 31. So to predict 31.8, we need a, we need a 32 and 32.5 are the inputs. So first I have to create a 2 time lag, and I have to see how my today's temperature correlated with yesterday temperature, how today's temperature correlated with day before yesterday temperature, how today's temperature correlated with the 3 days before temperature, with the 3 lag, 4 lag, 5 lag. Likewise, I try to see the correlation score. So which time lag correlation score? Okay, there are, see, application to application, my lag factor will change. Say for example, temperature data, my temperature data is highly sensitive based on, if I consider like 1 week lag, it could do a good job. May not be work very well for the trading data set. Maybe for a trading data set, I should at least consider my pattern of forecasting pattern is highly dependent on a 10-day lag factor or a 15-day lag factor. First of all, we need to investigate this lag factor. So which particular lag my data is highly correlated, those lag only you should consider it. For example, look at to predict tomorrow's temperature. Okay, considering previous for example, previous 6 months data, if I consider, that is not considered as a good lag, because if I consider the previous 4 months or 5 months, now it is almost like a rainy season. Okay, we are in the August or September, your monsoon is going to start. So as the monsoon season is going to start, if I'm going to consider June temperature or May temperature, that is not going to have bring any context to the present temperature condition. In that case, so the temperature has a certain pattern. Okay, at least for the Indian context, if I draw the temperature, typically January, February, and the temperature slightly rose to March, April, May, June, it peaks. Okay, and slightly slowingly drop at July, August, monsoon starts, and towards the December it's come down. Again, the same pattern will repeat for the next year. So this is the pattern. So to capture this pattern, I could have some meaningful context. So how many time delays if I consider, then I could have a meaningful forecasting. So I should not consider too much of time delays. Lag factor I should not consider. So probably you can take 2 weeks, could be make more sense for the temperature or for the trading data. For that, we need some domain knowledge will help us to understand how many lag, if I consider, I could have a meaningful forecasting. Again, for the gold prices or fuel prices, how many days lag, if I consider, I can have go with the meaningful forecasting. Technically, you can do this. You can create a multiple lags, and all you need to do is just you calculate the correlation score. Which particular correlation has given the highest correlation score, you can design that many lag models you can create. I just quickly show you. Anyhow, we will walk through this notebook line by line. I just wanted to show you how this correlation, okay, this lag autocorrelation score looks like. Just to get a quick idea. Look at this. Here I have plotted autocorrelation plots. What actually this autocorrelation plot is doing here, I have specified, consider 30 lakhs. Just I'm just specifying my time series values, which is a single column data. Okay, you don't need to manually prepare, like as I told you, right? T minus 1, T minus 2, T minus 3, T minus 4. Here I have defined 30 lakhs, means up to T minus 30 has been created. Okay, the current temperature is being checked with the previous temperature, lag 1. Okay, this is with the 0 lag. Can you see? 0 lag means, okay, your time series data set, your time series data set matched with the same copy of the time series data set without any time lag. Okay, it's just a replica of the same column, right? Say 30, 31, 32, 31, 30, 32. With the 0 lag means this is also 30, 31, 32, 31, 30, 33. If I calculate the correlation score, it is 100% matches. If I do time shift 1 time lag means, then obviously T minus 1 would look like this. Okay, 0, 30, 31, 32, 30, 30. This is a 1 time shift. 2 time shift, it goes like this, 0, 0, 30, 31. Obviously, okay, this guy, the correlation, how it correlates with 1 time lag, how it correlates with the 2 time lag. As you see, if I go with 1 time lag, 2 time lag, 3 time lag, my correlation, my dependency, if my time lag increases, maybe if I go with the 30 lakhs, look at this, my dependency decreases. It's around the correlation score is around 0.2. But however, if I consider the immediate yesterday temperature or something, actually this data is something related to sunspots. Okay, sunspot. We'll talk about this data set later. Any time series data in general, what you can understand, my immediate 1 time lag, it is strongly correlated, and if I consider the 30 lag or 20 lag, relatively they are less correlated. So by analyzing this autocorrelation plot, we can understand how many time lags are crucial for this application. Accordingly, that many sequence I can create, because your data preparation is very crucial for the modeling. So understanding this time lag is very crucial to prepare your data set. See, anybody can use, at the end of the day, you're going to call the model. Okay, the core, the programming content of your the core algorithm will be hardly some few lines, 4 to 5 lines. So at the end of the day, anybody can design this. But which are the crucial part is what? Your data preparation part. Your data preparation part, according to the particular application, is very crucial. Application to application, your data preparation part will vary. That is very crucial and challenging. That you master that skill. Okay, as the application changes, how do you represent your data? Because your core algorithm is going to be always almost the same. Okay, little bit of tuning you have to do according to your data structure, little bit of fine tuning you do in this core structure. Anybody can do that. So this part we'll be spending more time on understanding the data and preparing the data. This one, if you master the trade, okay, you can use this algorithm for any kind of application that you'll be working comfortably with ease. Okay, once I understand the specific number of lakhs, how many lakhs is needed for my application. Say, for example, I prepare maybe 5 lakh for this application. Sorry, t minus 5, t minus 4, t minus 3, t minus 2, t minus 1. So in early models, what they have done, something like this. They consider this as y, okay, this as yt minus 1 to yt minus 5. They consider as an input feature x1, x2, x3, x4, x5. This is considered as y. Similarly, okay, your single column time series data set is prepared like a 5 lakh column like this. Now what you have converted your single column data, you converted to a typical n cross p tabular data set. Okay. Early days, what they have done is using a simple linear regression model, or even I can use a ANN as a regressor. They use this as an input features to my neural network model, a simple feed forward model, and they try to map this y value as the output. For the next sequence, what is going to happen? Okay, this value, it looks like, okay, this output will push to here, this value will go here, this value will go here, this value will go here, this value will go. So this value will go out of this. Okay, that is your next record, right? And similarly, this record will come here and so on. So you have this. Early days, they have used a traditional feed forward model in a crude approach, but still they were able to manage this to 70% to 80% of performance level. They were able to achieve this. Of course, it may not be so so contextual, because you know it very well in this feed forward architecture. Irrespective of the order I present, okay, the model is learning this input in a crude fashion. Not here, it is not maintaining the order here. Even this x1, x2, x3, x4 in any order, if I present, my model will be learning in a different, the same way my model is going to learn. Whereas in your traditional tabular data set, something like x1 feature, x2 feature, x3, x4, x5, each one is highly independent features. Whereas here, being a time series data set, each value is highly correlated features. Each feature is a highly correlated features. Okay, your traditional feed forward model is not capturing any of the sequential context of this data set. So, but still I can make this model to work in a very crude manner to 70 to 80% of the performance level. I can make my model to work. The challenge is my model is not learning any sequential context. So first of all, that is what we are going to appreciate, how this evolution has happened. Initially, people have constructed this something like, even before a neural network model, they have used a simple auto-regressive model. They try to solve this problem as a simple auto-regressive model. Auto-regressive model in the sense what? We know the regressor performance. Your regressor as a function of y as a function of x1 feature, x2 feature, x3 feature. But this also I can model as a regressor, but only difference is, temperature as a function of temperature itself. Temperature as a function of temperature itself. That means what? Temperature today as a function of temperature previous few days. That is why it is called as an auto-regressive model. My dependent variable also temperature, my independent variable also temperature. So early day, people try to solve this kind of a sequence forecasting problem as an auto-regressive moving average problem. Gradually, they migrated to, okay, of course, we know that this relationship, if it is not strongly linearly associated, if we have some non-linear association between my x and y, obviously they tried with a traditional feed-forward neural network model. But again, the feed-forward neural network model, the limitation is not capturing the sequential context. They have introduced the feedback model. So recurrent neural network model. So we have understood how this evolution happens from a simple auto-regressive moving average model to a traditional feed-forward model to the feedback architecture. Okay, to reinforce these evolution, first to exercise, I'm going to give you some essence and idea about so how your time series data has to be prepared for the models. So I have taken this example to compare your traditional multi-layer perceptron feed-forward model with the feedback architecture. See, only in the next session, I'm going to talk about the mathematics behind the recurrent neural network model. Still, I have not entered into the core math behind your recurrent neural network model. First of all, I wanted to create the context first. Once I establish the context and how your model is going to handle your input, once you understand the context and the structure of the model, then I jump into the architecture and the math. Then you can easily relate to the application and context. So that is the purpose of creating this exercise, even before we jump into the mathematics, the core mathematics of this algorithm. So don't worry, the mathematics will be separately dealt. So once we finish this contextual understanding of this exercise. So to demonstrate this, I have taken one time series data set called as sunspot. So this is one of the popular data set. As you see, this is the data set which is taken from 1749 onwards. Look at the data. This is a daily, it is a daily recording. This sunspot is being calculated for mainly for the environmental to study the effect in the ozone layer, mainly for the environment, to study the environmental effect going to be, and to understand the core of the suns. These are some of the application context of this sunspot. Just imagine this is something like for your any time series data set you can relate to. Like simply you can understand something like a temperature. But we have some kind of a sequential context is there. So the one month to another month times sunspots, or 1 year to another year sunspots, there is always some pattern. The whole globe is following that pattern. And all the researchers who are working on this, environmental scientists, researchers working on how these effect of the sunspot, so year to year, so 100 years before how it was, and 50 years how it was, and last few years on the last 50 years how it is. To study all these, the sequential pattern, these sunspots data, the researchers were looking into. So let me load this data set, first 20 and the last 20 data set. Let me show you so that you can understand till what year this data set goes on. Okay, till 1983. So this is the last data set. So you can see this is a monthly record, right? It's a, for example, 1749 January month. Okay, every month on the first date they have recorded the sun. So 1 month report. So February month. Okay, the sunspot report is for the same year, February month. So March recording, April recording, May recording. It goes up to December. So next year, 1950, another 12 recordings. So per year they have done 12 recordings. So monthly one recording they have done. So this goes on till 1983. Okay, from 1749 onwards, it goes 1983. 1983 December. 234 years. Okay, 234 years per year, 12 recording. 2808 records in the time series dataset. So whenever you are reading your time series dataset, I will show you how this file spreadsheet looks like. So this is how your spreadsheet looks like. This one. In order, if you wanted to make your Python to understand, to handle this column as a date time format, I have to parse this as a, I have to tell my Python function, which is pandas function pd.read csv. Okay, I have to tell that parse dates. So to treat this index column, your date field index column should be treated as a actual date field, so that you can when you access it, you can really access this one like a year or with a month. Otherwise, no, by default it is going to consider something like a, okay, default it is going to either consider as a string object or a numerical object. So when we are treating this one like a string, string means it's a meaningless. So I cannot go and handle separately. Say for example, 1982, I wanted to access the all 12 recording of 1982 year alone, or I can say that 1982 particular month alone I want, this particular month alone I want. So I can easily parse this one like a date, year, month and date field. Just for an example, let me show you here. So once you pass this as a proper Python specified date field, then I can say, for example, I need to plot 1755 to 1770. 15 years. Okay, I'm saying that plt.plot, I wanted to see the time series pattern of 15 years pattern. In fact, we have the data of 234 year data is there. Or 20 years. If you don't parse this field as a date format in Python during reading, what will, no, it will show the syntax error. It will not understand what is S single quote 1755. Okay, you have to access the whole object at once. So for a particular year, you cannot access it like this. As an index, I cannot use it like an index. Even you can say in 1755. Okay, when I say 1755, all 12 recording is displaying. Say you can handle it like, for example, 5th month I need. Okay, it is going to handle that particular 5th month record. Suppose if it is a daily record, assume here per month we have only one record. Per month we have only one record. Suppose if it is something like a daily, every month I have 30 or 31 records. Even I can use the date field to pass this. Okay, for example, 1st of May till, I can pass the year field like this, 1755 colon on the May month. Okay, till first 5 days data I need. But here it is going to throw an error because we don't have a daily recording. It's a monthly recording. Suppose your data is a daily recording. Okay, because we don't have that index. We have only one record. No, that is why it's returning 0 here. But if you have a data on the daily record, so May month, 1st date, 2nd date, 3rd date. So all 30 records if you have, then it will give you the sequence of those values. Since monthly only one record is there, so This way I can pass 1755 hyphen. So 5th month to 10th month I can pass like this. So 5th month to 10th month. So it is returning me. So using the year field and month field and the date field you can access. So that is the benefit of parsing your date field. So because that is very important to analyze your time series data to have understanding of your pattern. Okay, what pattern your time series data set is following. See, for example, as you see, initial few years, this is your something around the 75th record. 75th record is starting from 1755. 75th record. This is around maybe I can say a 5th year. Okay, so starting from this, the 5th year, the sunspot level increases and again gradually decreases during 6, 7, 8 years. So you can have some kind of a pattern periodically again from this year again during this middle again the sunspot level increases and again gradually falls. So there is always the sunspot is following some pattern. It reaches some maximum value, it's coming down. It reaches a maximum value, it's coming down. After how many years it is having some maximum peak and it's going down. These kind of patterns we can investigate. Maybe till 1800 if you wanted to see, you can have some more duration. You can see some kind of a periodic pattern you could notice. In recent year, if there is any big changes that happen, till we have the data till 1983, right? In recent few years, if you wanted to analyze the pattern, maybe I can say last 1980 to 1983, because we have the data available till 1983 currently in this file. But there are some web resources are available even till 2000 data sets are available. So this is the pattern of the 1980 to 1983, this 3-year pattern. This 3-year pattern, you can see the sunspot levels is gradually decreasing in this. So 1983 till 2000 recent time, what is the pattern? Still it is a decreasing pattern or increasing pattern, we are not sure. But according to this data set, we can analyze till 1983. So how the sunspot levels vary. So this initial plotting, your time series plot will give you an idea about to understand your time series data set, the pattern in the time series data set. So afterwards, the second level analysis, what you need to do is you have to understand the time lag. How many time lags I'm going to utilize for this model. So to have the time lag plot, I have to use this autocorrelation ACF plot. There are two packages this autocorrelation plot can be plotted. One is using pandas package itself. Pandas.plotting function is available to do this autocorrelation plot. Another package is stats model graphics. So time series TSA plot, time series analysis plot. So here from here I can import this plot autocorrelation function. So what you need to say here, because S is what I have loaded my data, can access all the values using S dot values, and you can specify the number of lags you wanted to analyze. If you wanted to analyze only the recent 10 lags alone, if you wanted to analyze, you can say lags 10 and you can see the analysis. So the last 10 data, it is highly correlated with the last 10. Any particular sunspot, any month sunspot level is highly correlated with the previous 10-month pattern. Even if I take the previous 20-month pattern or even a previous 24-month pattern, it's 2-year. Whether my current month sunspot, how strongly associated with the last 2-year pattern of the sunspot. If you see the least correlation score comes around 0.4. So what I can suggest you, technically you can consider, okay, the lag factor, anything the correlation score above 0.5 is considered as a decent correlation score. Okay, I could recommend you can easily consider any lag value. Anything above 0.5 is considered as something decent enough correlation score to include those time lag into your model. So I don't consider the correlation score like 0.1, 0.2, 0.3 and all. It's a very weak level. It's not recommended to consider it. Okay, let me go few more time lags. Let me see what is the least score I get. Okay, 3 years pattern, how it is associated with the last 3 year pattern. You can see if I go up to 36 time lag, you can see these values are dropping very drastically. My score is going below 0.2. So below 0.2. Maybe I can restrict somewhere close to 30 if I restrict. If I take 30 lag, so the least score is, even at the 30th lag, my least score is around 0.2. So it is purely based on the experimentation basis only. So don't consider any value close to 0, 0.1, 0.2 and all. Strictly speaking, any time lag above 0.5 is sufficient if you are using a very powerful feedback based model. Since we are not, initially we are not going to use any feedback based model. A simple crude model, feed forward model itself, we are going to train. So for a safer side, I'm going to take a few more lags till with a cutoff 0.2 and above. So I'm going to consider 30 lags. Maybe once you have a very strong feedback based model, maybe you can consider the cutoff 0.5 and above. You can see the number of lags. For suppose if you wanted to consider 0.5 and above, probably I would recommend the lags up to, okay, the lag up to, we can say around the 15 previous 12 to 15 months. If you consider, that means strictly you can consider 1 year to the maximum 1.5 years. So 1 year to 1.5 year pattern, sunspot pattern, if you consider, that will be a highly correlated information. So that will have some kind of a meaningful forecasting context. Going beyond that, it is going to gradually reduce the context. Your sequential context is going to drop, going more than 1.5 years and above. So this is the second important component. Once you understand your time series pattern, the second component is what? Understanding the outer correlation. So first let us demonstrate how to use a classical autoregressor model. I told you the classical autoregressor model works as a linear model. So we have something called as a stats model, PSA AR model package. I have imported AR. AR stands for autoregressor model. In autoregressor model, all you have to tell that which sequence of pattern you are going to train, which sequence of pattern you wanted to use it for the forecasting application. Unlike your tabular data set, so far the applications, whatever we have built your tabular data set, we have used a train test split. You know, the train test split is going to take your record in a random order. You know it very well. Say for an example, I have 1, 2, 3, 4, 5, 6, 7, 8 records. Assume I have 8 records. If my train test split is going to divide a record, like if I say some 70-30 split, maybe record number 2 and record number 7 is reserved for the validation, and 1, 3, 4, 5, 6, 8 is used for the training. For a tabular data set, there is no timestamp association. It is okay to pick it randomly. But here we have the data which is on the timestamp. Okay, I cannot use train test split to divide the data on a random fashion. I will be losing the time context. So what I need to do, literally, imagine this is my time series data set having following some pattern like this. What I'm going to do, always remember, whenever you're going to train the model, you reserve certain portion of the sequence for the training. Okay, certain portion of the sequence use it for the validation. Imagine if you have a 10-year data sequence. Assume if you have a 10-year data sequence, probably I can use the 8-year data sequence for the training. The recent 2 years data sequence, I can use it for the validation purpose. Recent 2 years. So sequentially, you have to divide. So what I do here is, you can see why the way I define my train and test data. I'm just leaving the last, I'm just reserving the last 17 record, maybe last 1 year, 1.5 years roughly, last 1.5 year record I reserved for validation. Okay, so last 17 months record alone, I'm going to use it for the validation. Except 17 record, the remaining records, we are going to use it for the training. So totally we have got 2802 plus 17, 2819 records. So I manually define my training and testing. So first 2802 sequence for the training, the last 17 record reserved for. It is our wish. If you wish last 2-year pattern, 1982 and 83, if you wanted to reserve, accordingly number of patterns you can stop. Or 81, 82, 83, last 3-year pattern, if you want, you can say 36. Instead of 17, you say minus 36. Here also minus 36. That means the last 36 months data you are reserved for validation. So after splitting the record, okay, I check the shape. So now you define your model, AR model. So we have taken 30 time lags, right? 30 time lags we have taken. So whenever out of the 30 columns, okay, out of the 30 columns, one column will be always used as Y, the remaining column will be used as X. Okay, so T is referred as your Y from T minus 1 till T minus 29 will be considered as your independent variables. So we have got 29 inputs, isn't it? 29 inputs. See, the way I presented my training and test data, I just tell how many records, till what sequence we are going to use for the model. This analysis, we are doing the lag association just for our internal understanding. Okay, but while defining the AR model, I didn't anywhere I didn't specify the number of lags. If you notice, in the AR model, nowhere I define the number of lags. I just leave it to, okay, I just leave it to the model itself. I'm just leaving to the model itself to take the most prominent number of lags. I'm just leave it to the model. When I leave it to the model has taken, in fact, model has considered 28 lakhs. 28 lakhs. Whenever I say, after fitting the model, when I say K underscore AR, it is returning 28 slopes plus one intercept, including one intercept, it is computing 29. One intercept followed by 28 slopes. So your model equation would be something like this. Yt is equivalent to beta naught plus beta 1 xt minus 1 beta 2 xt minus 2. Let us consider beta 28 xt minus 28. It has considered 28 lakhs. It has considered. That is why we have got 28 slopes, including one intercept. So when I say dot params, including the intercept, it will return. So I say length of what is the total number of model parameters this the default AR model has taken. So what is the default model has taken? 28 lakh means your default lag is being designed in such a way that, okay, they have given the cutoff is somewhere close to 0.2. So if the correlation score is 0.2 and above, your default auto-regressive model is considering all the 28 lakhs value it is considering. So going beyond 28, you can see the value touching 0.2 and it's going, in fact, it is less than 0.2, 0.19 and all it's coming to. So that is why it is taking point. So the default auto-regressive model is considering roughly, it is considering the lag in which the correlation score is 0.2, at least 0.2 and above, it is considered. That is why the default number of lakhs taken by the AR model is 28 lakhs. Anyhow, at the end of the day, we are not going to use this AR model on the current context. In the current context, we will be using more advanced model. I just wanted to show you how early days the researcher has solved the time series data set even before our advanced neural network models. So once your model has learned the model parameters based on your training samples. Okay. Now I need to do the predictions. Okay, when we do the predictions, I say model, the fit model, right? Model underscore fit, because this is my current model object. After fitting, I kept my model object name as model underscore fit. So I use model underscore fit to predict. Now this portion is very important. How do we define, pass these parameters inside? What is your start sequence? What is the end sequence that you have to tell? Okay, let me explain with a small sequence. Our actual length of the sequence is 2807 something. Okay, just to simplify this, let me take it like this. Assume I have reserved the last 1, 2, 3, 4. The last 4 record is reserved for validation. Assume. So initial 1 to 10, maybe I have used for the training purpose. Okay, so my start of the sequence, because when you define train and test data set, what you have defined, this portion is a train. Okay, this last 4 sequence is being defined as a test. So the start sequence is start from the 10th index, length of your training sequence, because actually it is taking from 0 to 9th index. So your length is going to give you the 10. Length is going to use as a 10. That means the value 10 will be written. So the starting index will be 10. Because your first 10 is being accessed up to 9th index, isn't it? Starting from the 0th index in Python up to 9th value, it is being utilized for the training. But 0 to 9, when you ask what is the length of 0 to 9, when you ask what the length function will return, the length function including the 0th index, it is going to return 10. The 10 is being used as a starting index. So the starting index of my test sequence is going to start from the 10th index. So that is the meaning of the start. So the ending index is what? The length of the train plus length of the test minus 1. So that is the end sequence. Because for the last sequence, I don't have the next value to check it, right? The maximum I can check up to this value, I can check what is the next forecasting. And for this one, if I use this as part of my previous input, I can use this for checking, predict this. Up to this maximum, I can predict this. Okay. So since my data get closed at the 14th index, I cannot use the last value for the prediction purpose. So last but one, till the last but one, I'll use for the predictions. And the last parameter is dynamic false. Okay, I'll come to this. I'll tell you what is the meaning of this dynamic false. So what is happening here, how the model is going to do the predictions here is, okay, for a better understanding, let me use the normal index. I'm not using a Python index. Okay, so record number 1 to record number 10, model has already learned. Now we wanted to start the predictions from record number 11. Okay, to forecast, okay, what is the predicted value and what is the actual record number 11, that actual sunspot will be there, right? Now I wanted to see what is the forecasted sunspot at the 11th position. So how model will do the forecasting? Since the demonstration I have taken the 10 sequences, assume that in our case model has taken the previous 28 lag it has taken, right? Maybe for this demonstration, maybe I have built my model. Model has taken the last 5 sequences. Okay, the 5 lag it has taken means model will use this as one input, this as second input, this is a third input, fourth input, and fifth input. It will plug in and it will try to forecast this value as the first forecasted value. Once it is forecasted this value, next model has to predict the next value, isn't it? 11th value is forecasted. Now it is going to predict the 12th value it has to forecast. In that case, now we'll come to the meaning of dynamic false. If I say dynamic true, means what will happen now? Whatever the forecasted value, say if the actual sunspot is something like 80 and the forecasted value is 82. When I say dynamic true, model would consider the forecasted value for the 12th record prediction. Okay. Whereas when I say dynamic false, it will use the actual value available in the 11th index, 11th position. It will use 80 value. It won't use the forecasted value to predict the next value. So that is the difference between dynamic false and dynamic true. So first, when I say dynamic true, once again I tell you that dynamic true in the sense, now to forecast the 12th value, so what model should use? Model should use previous 5 lakh. This time the previous 5 lakhs including my previous output, right? Now your previous output is going to be part of your input now to forecast the 12th value. So your previous output is part of one of the input. So in dynamic true, what will happen? Whatever the forecasted value will be substituted here. That is dynamic true. Whenever I say dynamic false, instead of substituting the forecasted value, I'll be using the actual value. Then it is called dynamic false. So either way, you can say that dynamic true or dynamic false. It's up to the design spec. Okay, whether you wanted to use the actual value or the forecasted value. But dynamic true would be more like a real time match with the real time scenario, like instead of using a dynamic false. But either way, we can run and see the results and the performance. And now next to predict the 13th location. Now this time model would consider the previous 5 lakhs could be taken like this. 1, 2, 3, 4, 5. So next to forecast the 14. So we have taken totally 14 records, right? Up to 14 we can forecast the previous 4 lakh. So in that case, when I do the predictions for the reserved 17 location, you can see the forecasting done for the reserved 17 values. These are the predictions done for the reserve, the last 17 months, the forecasted sunspots. If you wanted to compare with the actual last 17 values, or these are the actual last 17 values and these are the forecasted values. Can you see the actual 107.6 model forecasted 103.76. In the actual 118.8 model forecasted 99.45, not that great. 94.7 model forecasted that value 97.3. 98.1 model forecasted 103. So instead of comparing one by one, what I'm going to do, because each and every value, the actual is something, but the forecasted value is something. So there is some difference. Okay. Now I wanted to report the difference as what is y actual and y is forecasted value. So for the first case, the actual is 107.6. The forecasted value is 103.7. Roughly, we have a difference of 4 sunspots. Okay, the difference is roughly 4 sunspots. Another record, we have a difference of 5 sunspots. Another difference, we have a difference of 3. So now the forecasted value is lesser than the actual. You got the difference is in the positive. Suppose the forecasted value is bigger than the actual. Okay, the forecasted value look for the third one. The forecasted value is bigger than the actual. This time the difference is around -3, no? Roughly -3. So sometimes the difference is 5 difference. Sometimes the difference is -2. Sometimes the difference is 1. Sometimes the difference is -8. Sometimes the difference is +8. Now I wanted to know what is the average difference. Okay, since some differences are positive, some differences are negative, what I do, I just square all these differences. Square all the differences and then I take the average. Okay, so instead of taking the average difference, now I'm calculating the differences, the squared differences average I'm calculating. But I wanted to report the average difference. So to remove the effect of squaring, we are going to take the square root. So y actual minus y cap forecasted value squared sum divided by total is going to give me the mean squared error. Okay, what that mean square error is going to give me, what is the mean value of the squared difference. But I wanted to know what is the mean difference. So to remove the effect of squaring, I have to apply square root because I only squared for my convenience. To remove the effect of squaring, you apply square root, you report the score as a root mean square error. So finally, your root mean square error is going to tell, okay, sometimes the model over predicts the sunspot, sometimes model under predicts the sunspot. What is the average difference? Okay, so the average difference is being reported in the form of a root mean square error. If the model forecasts the model using 28 time lags, using a simple auto-regressive model, the forecasted model, I just map with the actual values. If you see, the red one is the actual value. The blue one is the forecasted value. See, you can notice your model is simply calculating the previous few lakhs average values. You can see it's average out. It failed to capture the pattern actually. Your simple AR auto-regressive model, it's failed to capture the actual ups and downs. Okay, you can see the sunspot increases if there is a fall. Again, there is an increase, there is a fall. There is an increase, there is a fall. The original pattern is not being captured by a simple AR model. Though it utilizes the 28 lakhs. In fact, the 28 lakhs, the correlation score is above 0.2 it has taken. So we conclude that AR model is not capturing any of the ups and downs. The original pattern is not being captured. Of course, it has done some kind of a very crude predictions, and also that you wanted to report in the form of a root mean square error. I just compute the root mean square error for the last 17 predictions we have reserved for the test data set. You can see the average difference is around. Our model forecasts the sunspot with the average difference of around 18 sunspots. If you go with the simple auto-regressive based model. See, also you can do the customized representation of the time lag if you wanted to manually generate. You don't want to go with the using the AR function. Instead of using the built-in AR function, if you wanted to write your own customized algorithm, you have to generate the lags, isn't it? So to generate the lag, you can use a for loop and you can generate the lag. So I have given a template to generate the time step according to your customized representation. If you don't want to depend on any of the built-in library. So here I have just used a loop to generate the lag. So I create a for loop to start the range from, suppose if you wanted to give 20 time step as a lag. See, I start my I index starting from 20. What is happening is initially my X train and X test are empty list. What I do from my training record, I am accessing I minus 20 colon I. What do you mean? The first I value is 20. So basically it is considering. So 20 minus 20, what happened? 0th index to 20th index is used as my input. Okay, that is my first record, isn't it? My first record of X train. What is the corresponding Y value? The corresponding Y value is, okay, you know, in Python index, whenever I say 0 colon 20 means 0th index to 19th index alone it will take. So when I say train of I means the current I value is 20, the 20th index is used as my Y train. Okay, up to the 19th index it's considered as a X train. This is going to be my first record. How it is generate the second record? Now the I index will turn to 21 now. This time, okay, 21 minus 20 colon 21. That means 1 colon 21. This time it is going to access the value from 1 colon to 20th index. Because this time the 0th index will be pushed out, right? Now starting from the first index, it goes on till the 20th index. That means your 21st index will be treated as your Y train. Likewise, you can create your X train and Y train according to the number of lags you want. You can use this loop to generate your own sequence. So this will create your customized lag sequences. Okay. So if you wanted to explore your conventional model using your customized lags, you can explore using the template I have given. You can use your sklearn linear regressive function also. You can import. See, as long as you created your X train and Y train, even I no need to depend on this AR function itself. From sklearn linear model import linear regressor, I can build a simple linear regressor model also. But that model also behave in the same manner it will behave. It failed to capture this ups and downs pattern in the original sequence. So now we move on to, okay, TensorFlow design. That is more contextual here. Okay, I go with typical feed-forward model. So how to construct a feed-forward neural network model for this application? Look at your structure of this architecture. So far in all the algorithms we have seen, we started with model is equal to sequential. Immediately I have given the next layer is, the first layer is dense layer. That means I have used one hidden layer with 100 neurons. With 100 neurons. One neuron in the output layer. How many neurons it is going to use in the input layer? The 20 time lag it is using. This 20 time lag you can create, okay, using the customized template I have given here. Then only can pass your input shape. My input shape should come in the form of a 20 time lag. So to create your X train, okay, according to what spec, how many lags you want, that many lags you create, and you have to present your data. So 20 input it is going to come as an input. Remember, in your TensorFlow design, okay, you never pass how many records you are going to pass. So that is the beauty of your TensorFlow layer. It will be automatically understand. You don't need to explicitly tell how many training record you are going to pass. So internally, if you see, your input shape is defined something like a none comma, okay, none comma 20 comma, I would say like channels. So this is the default design. What do you mean by this? This none will be always treated as, you don't need to tell explicitly how many training record you're going to pass. So your layer will understand dynamically, irrespective of whether you wanted to train 2782 records or even 10,000 record, doesn't matter. Even 1 lakh record or 1 million record doesn't matter. So dynamically it will understand how many records you pass. Which is more important is, okay, per record, what is your dimension? Whether your dimension is a vector or it's a single channel vector or a multi-channel vector. So when we use EEG data in the one of the previous session, okay, though we have applied this EEG as a single channel, okay, there is an option for us. Even if you want to pass a multi-channel EEG data, you can specify, say for example, your brain signal is being recorded at 3 different places in our brain. Okay, this is from the head region. Okay, one recording I have taken from the frontal lobe, another recording I have taken from the occipital lobe, and a parietal lobe. At 3 different places I placed the sensor, and for the same patient I recorded EEG pattern as a 3-channel. And this is how you have recorded for each patient. You have a 3-channel record. Here you can specify your input shape as, okay, what is the length of your sequence? What is the length of the sequence? And along with the number of channels. For example, the length of each EEG channel is, for example, 10,000 samples. Here you have to say 10,000 samples. It doesn't matter how many patients you have recorded. Suppose you have recorded this with some 500 patients. Basically, you need to train 500, the EEG pattern acquired from 500 patients. You have to train the model. This 500, you don't need to tell explicitly, but what you have to tell, what are all the information you have to tell? You have to tell the length of the sequence, which is 10,000. And is it a single channel time series or it is a multi-channel time series? That you can specify. In that alcoholic, non-alcoholic EEG session, when we discussed build the model, there we have used single channel. Having said that, this layer is being designed to handle even multi-channel also. Like image also the same scenario. In malarial dataset we have presented, okay, malarial dataset we have presented 100 by 100 is the dimension and number of channel is a color channel. But MNIST dataset, when we presented the data, we have presented 2828. It is a mono channel. It's not a color image. But even for this, your first dimension is kept as a none. Architecture will understand any number of images you can train. So this one you don't need to tell explicitly. So the basic design is you can present your data as a 1-dimensional or a 2D, but here is a 2D, but here it is a 1D representation. So this is about the channel. So here also it is a time series data set. Some of the time series data set are being recorded at multi-channel analysis also you may do some occasions. Say for example, you wanted to do some kind of a weather analysis. Okay. A multivariable time series data set. What is mean by a multivariate time series data set is something like okay, first Jan, wind velocity. Okay, wind velocity, humidity, a millimeter of rainfall. Wind velocity, humidity in the atmosphere, millimeter of rainfall. 2nd January, what is the wind velocity, humidity, and millimeter of rainfall? This kind of a time series data set also I can model. In this case, okay, in this case, you are not going to forecast the millimeter as a function of the previous few samples of the millimeter. In this cases, you are going to use this variable as a two-channel variable, two different variables. You wanted to use this as a two variables. In this case, you can define it like this. So millimeter of rainfall. Okay. So my current today's millimeter of rainfall is dependent on the previous past few days wind velocity and humidity. Okay, including your previous few days rainfall also you can consider. This is called it's a multivariate time series problem analysis. Okay, to forecast tomorrow's rainfall, I'm not only use the previous few days rainfall, I'm also going to use the previous few days humidity level and previous, say for example, previous 10 days pattern, the last 10-day wind velocity pattern, the last 10-day humidity, the last 10-day rainfall also. So that would give me the better, closer approximation of the forecasting, isn't it? So this kind of problem, I may pass multi-channel data also here. So for that case, you have additional information, but here we have only one information along with sunspot. Maybe if you have few more variable also, your TensorFlow framework would accept for multivariable time series analysis also. So in that case, you have to prepare the data set not with a single column. Okay, it will be having a multiple variables will be come into picture. So before I run this model, I have to prepare my data according to the sequence. So 20 time lag I have taken 2782 by 20, and the respective y values are this. This is 20 lakhs will be taken as the input, and this is my y value. Here we are constructing a feed forward model. We are constructing a feed forward model. A feed forward model with 20 lag input is coming as an input. Without this, see here, listen carefully. Without this layer, if I run this deep learning model, it almost behave like our ER model, because our auto-regressive model has a linear characteristics, does not have a non-linear characteristics. Okay, so now, but we are considering that as a neural network model by introducing one hidden layer, which is of course have some kind of a non-linear characteristics. Okay, could better capture the pattern of the original time series. What are the changes if I notice in the design in contrary to a classification model? Let us notice the differences. This loss function. In fact, the housing value we have constructed one neural network model as a regressor model to predict the house price. There we have used the loss function as a mean square error, MSE. Whereas the classification problem for binary, we have used binary underscore cross entropy. For multi-class, we have used categorical underscore cross entropy. Since we are using the deep learning neural network architecture to forecast the sunspot values are in the numerical, continuous numerical score. That means we are running a neural network model, multi-layer perceptron artificial neural network model as a regressor. Same design, if you wanted to construct using a sklearn library, what library I should use? MLP regressor I should use. MLP regressor. So just one-liner function. My model is MLP regressor, hidden layer underscore sizes is equivalent to, what is a hidden layer? It's just only one hidden layer with 100 neurons. That's all. In sklearn version of designing, this is just a one-liner definition of your model. Okay, model is equivalent to MLP regressor with hidden layer sizes is 100. Only one hidden layer with 100 neurons. So this is my model. Model.fit, model.predict. That's all in sklearn. But in a TensorFlow deep learning architecture, the design goes with like this structure. This is with the TensorFlow Keras framework. Here I'm using a optimizer as Adam optimizer. With the 300 epoch, we are training this model with the 300 epochs. So already I ran this with the 300 epoch. In meanwhile, let it run. Here it is running here. Okay, you can see the loss gradually. You can see the loss, how the loss is being gradually decreased. Initially, your loss is somewhere, your mean square error is somewhere around. See, initially it starts with 3,828. It gradually converges. 1,200, 900, 800, 700, 600, 500, 400, 300, 290. It converges. Okay, let it goes on. In the meanwhile, okay, after training this, when I do the prediction, okay, with the neural network model, of course, it's not having a feedback behavior. Even without the feedback behavior, when I introduce a hidden layer with a non-linear characteristic, earlier autoregressive model is a linear model behavior. Whenever I use a linear model behavior, the model fails to capture the ups and downs pattern. But the moment I use a non-linear model, you can see a multi-layer perceptron model predicts, forecasted the value. Your original pattern is being captured. Pattern is captured, not just capturing the average value. This is something like your autoregressive model sampling calculated just an average like a straight line. Something I can say is underfit model. So this is something like an underfit model. Whereas your multi-layer perceptron, even with the one hidden layer architecture, okay, now I think the 300 epoch is over, I guess. Yeah, all 300 epochs got over. You can get your model summary. You can see, I told you always the none will be considered as your data, number of samples you pass, number of records you present. So how do we got this 2100? Because it receives 20 inputs, right? 20 input. So 20 inputs connected to 100 neurons. 2000. Each neuron, 100 neurons in the hidden layer will have one bias. Okay. So 2000 plus 100, 2100. Okay. In the output side, you have got 100 neurons connected to only one neuron. So you have got 100 weights, including the weight of the bias, 100 plus 1, 101. So the total number of model parameters, 2100 plus 101. So totally we got 2201 model parameters. model is updating. That many weights model is updating. And now training is over, right? My test data also I should prepare according to the lag representation, isn't it? So my test data also I prepared according to the lag, not as a one column sequence. Look at my X test is being prepared as 17 by 20. Model.predict, I pass the X test. 17 values are being predicted. Y hat is having the predicted value. And Y test is having the actual value, and Y hat we have got the predicted value. So I am plotting Y test with Y hat value. We have got closer value, but however there is a slightly, there is a lag is there, there is a time shift is there, but still it is capturing the ups and downs pattern is being captured. Whereas if we include the feedback mechanism using a recurrent neural network model, we can avoid this lag. We could avoid this lag as well as the original pattern. We can preserve the original pattern as well as the lag also we can avoid. The performance of the model will be much improved. So how by incorporating the previous state output as a feedback input, your model is going to learn in a better way because it is going to hold the context also into picture. And what is the underlying mathematics which is governing that process? All are very interesting to discuss in the day after tomorrow session when we discuss. I will put forward all the mathematics of the recurrent neural network model. Also, I'll tell you why the conventional recurrent neural network model is not recommended to use as it is. So we'll be using certain customization of the recurrent neural network. See, the core engine is based on the recurrent neural network, but there is a practical difficulty in applying the recurrent neural network as it is the real life problem. So for the practical usability factor, we little bit fine tune the traditional recurrent neural network in the form of a long short-term memory. Thereby, we are using the best way we can leverage the recurrent neural network in the form of long short-term memory. So other way I can say long short-term memory is a feedback-based neural network model, which is I can consider as a customized version of recurrent neural network model is a long short-term memory. So what kind of customization we do, why we do that customization, everything you will understand once you understand the complete mathematics of recurrent neural network. So I will be discussing on the Thursday session. So once we appreciate the mathematics, understand the limitation factor and what kind of customization we do in the LSTM. Once we figure it out, then I will use the LSTM model to solve a forecasting problem. So initially we will solve a time series data set. I will implement LSTM model followed by a text sequence forecasting model. The kind of application we are using in our modern day mobile phones and the email, what the technology they're using in the email reply options when we do, how the sequence of text, if you pass as the input, how it predicts the next sequence of text it predicts. So that application, before we apply LSTM model for the text sequence forecasting, we have to run through the numerical data set. This time series data set, we'll appreciate how LSTM model do the forecasting, and it is doing a reasonably time sequence memory. It is going to hold the time sequence memory. So the sequential memory also captured. So your traditional multi-layer perceptron model does not hold information about the sequential context is not being preserved because the previous state output is not fed as an input. Your model is not literally not storing the memory. It's something like a crude memory. We train the model like something like the crude memory. Whereas in a recurrent neural network model, we are going to have something like the sequential context also we are going to put it in the memory. So that's the scope of. So today's agenda is not the complete mathematics of the recurrent neural network. First of all, you should understand what is the scope of recurrent neural network model, to what context come into the picture. So I have established the context here. The context here is for the time series dataset. So why the conventional model fails on the time series? Conventional linear model like autoregressor model and the multi-layer perceptron deep learning model, they fail for the time series dataset. And subsequently, we are going to understand how a recurrent neural network model is going to fill this gap. So how exactly the recurrent neural network is going to fill this gap of the sequential context that memory is going to utilize here to solve this kind of a problem. So any quick questions that we can share if you have any questions on this contextual understanding of recurrent neural network in contrary to your traditional multi-layer perceptron neural network model. In terms of architectural differences, the major difference is what? In our traditional multi-layer perceptron neural network model does not store the memory of the previous state output. Memory is not storing. That is the important difference. Okay, this is what the architecture goes on, right? This is the hidden layer. This is the output layer neuron. We present the data. Okay, of course, you present the data something like xt minus 4, xt minus 3, xt minus 2, xt minus 1. Okay, this is what your x temperature. Today's temperature is based on the last 4 days temperature. And the next 4 days temperature, you are telling the model to memorize in a crude manner. Okay, and moreover, there is no any order you can train. No, doesn't model will not understand whether you present a t minus 4 here or t minus 2 here. There is no sequence is preserved here. And moreover, this output is not fed as an input here. Okay, this memory is not there in your traditional feed forward model. Okay, without this feedback memory, model has learned your multi-layer perceptron model, your deep learning model with one hidden layer architecture with the 100 neurons we have trained it. Without that feedback memory, model has learned the sequence in a very crude memorization. There is no sequential context memorization. Whereas if you memorize with some sequential context, okay, the memorization will be like something like a better memorization. Any questions? So clear what we have discussed in this session, I hope.
Yeah, it's clear.
Makaranthi, you can watch the previous session recordings.
Sure, sir.
Yeah, to re-emphasize your ideas on the back propagation algorithm and stuff like that. See, even in the recurrent neural network also, we are going to propagate the error back. The same mathematics is going to come, but additionally, okay, the weight update is going to happen in the feedback loop also. The weight update happens, but the core mathematics, whatever the back propagation mathematics we have seen in the traditional feed forward architecture, that mathematics is going to come, but additionally, we are going to work out the weight update in the feedback loop also. We are going to do that weight update. So having said that, your feed forward back propagation neural network mathematics, we are going to utilize 100% in the feedback architecture also. Okay, for the feedback architecture, we are not going to use something special mathematics. The same mathematics, your delta calculation, error delta calculation, everything is additionally. Okay, this is what your model is output. In the feedback also, I have some weights being connected. This weight also being updated, okay, along with the error delta calculation. So your basic, your calculation of your delta calculations, everything remains same. Everything remains same. The mathematics all your d minus o into 1 minus o, everything remains same. Only your structure of your, only I'm going to change the hardware. Hardware wiring alone I'm going to modify. Okay, the logic, or I can say the software, which is software, your learning style or learning algorithm, I can say the software. Hardware is something like the architecture, the wiring. Okay, only I'm going to modify the wiring little bit. I'm going to modify the wiring, but the software is going to be almost the similar software is going to run on the modified wiring. So that what is the modified wiring and how that software, how that same learning algorithm is going to run on the modified wiring, that we'll be seeing in the next session. So I will meet you on session 10 with a more interesting discussion on the recurrent neural network and LSTM model. I will meet you on session 10, Thursday, 7 o'clock. Okay, good night.
Thank you, sir.